Question 5, Part B. Figure 5.3 shows the poles of a powerful electromagnet producing a uniform field in the gap between them. The dimensions of each pole is 10 centimeters by 8 centimeters. So this bit here is going to be the area. There is no field outside the gap. A circular coil of 80 turns, so that's going to be capital N, is placed so that it encloses the total flux of the magnetic field. The current in the electromagnet is reduced so that the field falls linearly, so this is B, from 0.2 Tesla to 0 in 5 seconds. Okay, so what I'm getting a handle on here is we've got a dB by dt of 0.2 divided by 5. This is going to appear somewhere later on, I'm sure. Calculate the initial flux in the gap and hence the EMF generated in the coil during this time. Okay, the initial flux in the gap is a bit odd, so flux equals B times A. That's going to be 0.2, the initial B field, times the area, 0.10 times 0.080. And that, on my calculator, is 0.0016 Webers. Induced EMF is equal to the rate of change of flux linkage according to Faraday. This is going to be dNBA over dt. N and A are staying constant, and it is the B field that is changing over time. So N is 80, A is 0.10 times 0.080, and B is changing from a high of 0.20 all the way down to 0, so minus nothing, divided by 5 seconds is how long it takes to make that change. And then plugging this into my calculator, I get 0.0256. As all the numbers in the question have been given to 2 sig figs, really I should be recording that to 0.026. So my final answer, the induced EMF, is going to be 0.026 volts. Part 2. The coil is part of a circuit of total resistance R so that a current is generated in the circuit while the field is collapsing. Draw on the coil, figure 5.3, the direction of this induced EMF. Okay, I'm going to need the right hand rule for this. And what's happening is we need to apply Lenz's law. So the current induced in this coil is going to oppose the change that causes it. And the change that's causing it is that this B field is getting less and less and less. So the induced current is going to want to reinforce that to stop it from getting less and less and less. So as the field lines are currently pointing in this direction, that's what the current in the coil is going to try to achieve. So my fingers are pointing in the direction of the current. So I don't know how to really indicate that nice and clearly. So I'll just draw several arrows to show that the current is flowing in this direction. Just as an aside, if the B field was getting bigger, then the coil will want to oppose that, and so we'd line up our right hand rule the other direction. Anyway, so that must be worth 1 mark, I presume, of these 2 marks down here. This part, state how you applied the laws of electromagnetic induction to deduce the direction of this current. Only 3 lines and 1 mark. Good Lord. Well, it was an application of Lenz's law and the right-hand rule. The induced current will oppose the changing magnetic field. I removed field and put flux. The changing magnetic flux that causes it. As the flux is reducing, the induced EMF and the induced current will want to oppose that change by producing a field in the same direction as that of the magnet.